Move on to section 6.2, termination with resistive load. In section 6.1, we obtained a general solution to the transmission line equation for the lossless line as given in equation 6.20a and b. And as we can see here, in the transmission line, the signals that we are interested are voltage signal and current signal. And as I already mentioned, in the transmission line, we are dealing with a one-dimensional propagation problem. The signal, the voltage signal and the current signal are going either to the positive direction or the negative direction. Therefore, as the slide shown, the solution can be divided into two parts. For the voltage, it can be divided into V plus, which refers to the signal that goes to the positive Z direction, and V minus, that is the signal that goes into the negative Z direction. And the solution, the total voltage, will be the summation of the V plus and the V minus signal. All right? And as to the current signal, again, it can be decomposed into the I plus and the I minus part, which stands for the positive and negative going current signal. And there's one additional condition that we know is in the transmission line, the voltage and the current shall remain a ratio, that is the characteristic impedance of the transmission line. So therefore, in 628b, the I plus and the I minus signal are replaced with V plus over Z sub 0 and V minus over Z sub 0. Okay, so we use voltage signal as well to represent the current signal, the total current signal. So we use V plus and V minus to describe both voltage signal and the current signal. Okay, so to put it in a more simple way, we can write down the voltage and current relationship as these two equations. Okay, V equals to V plus plus V minus, and I equals to V plus minus. Be careful about this. This is the minus sign, which is critical to describe negative Z direction going current signal. Okay, so for the total current, that would be V plus minus V minus divided by Z sub 0. Okay, and as you can see here, in the parameters for V plus and V minus functions are a little bit different. If you take in the derivative of the parameters within V plus and V minus functions, you will end up with what? You will end up with the VP, the phase velocity, the propagation velocity of the signal within the transmission line. And this part you will end up with minus VP, which means the signal propagating direction is toward the minus Z direction. Okay? So using voltage and current, we can characterize the signal within the transmission line in a simple and straightforward way. All right, so here are the relationship we used in the previous slides. That is, the I plus equals to V plus over Z sub 0, and I minus equals to the minus of V minus over Z sub 0. The next thing we will look into is the power flow associated with the signal within the transmission line. For the positive Z going signal and power. The P plus is the power going to the positive z direction. And by definition, it should be the product of V plus and I plus signal. And you can replace I plus with V plus over Z sub 0. And you end up with V plus to the square divided by Z sub 0. Looks familiar. That represents the power going to the positive Z direction. But you need to be a little bit careful about this. This P plus is the so-called instantaneous power. Instantaneous power, okay? So it doesn't matter the V and I signal are sinusoidal signal or pulse signal or any types of the signal. So this is the so-called instantaneous power. If the signal are sinusoidal ones, sinusoidal signal, then we will be more interested about the so-called time average power. So for time average power in transmission line with sinusoidal signal, then the time average power will be what? Half of the V to the V square over Z sub 0. Okay? So if this is sinusoidal signal, then the time average power, you will have the 1 over 2 constant in the front. But for instantaneous power, it's just V to the square over Z sub 0. Okay? And you can do the same thing for the negative, for the propagating signal. That would be the P minus. And again, it's defined as the V minus times I minus, and equals to the minus of V minus to the square over Z sub 0. So that represents the instantaneous power of the signal goes to the negative Z direction. Okay? All right, so let's consider a transmission line model. That would be the first transmission line model that you will look into in this course. That's remind me of my first class in the United States. Okay, I'll try to tell this story in English. Okay. So in 1997, I went to the Ohio State University. Then on the first day of my first class is the microwave engineering. So we were studying all topics pertinent to the transmission line stuff. My instructor, my lecturer is a French professor, okay, and his name is I forgot his name. I really forgot his name. All right, okay. And anyway, okay, he's a young professor, back 20 years ago, yeah, and he comes from France, okay, but of course he speaks English during the class. And unfortunately, he just speaks about 10 minutes of English in the class. After that, he speaks French. Well, he still speaks English, but a very heavy French accent. So I keep continuing to, so of course, the first class, my first class in English, I didn't get everything, But I understand, I'm aware that there is something very important. He keeps telling Jinihato. So what is Jinihato? Okay, I know it's important because I heard that Jinihato for over 20 times in 10 minutes. So I look at the circuit. Can you tell me what is Jinihato? Then I realized, Jinihato is generator. That's the signal source over here. Well, Jinihato, because French, the R in French is oh, Jinihato, okay. All right, so this is a very simple transmission line circuit. It can be divided into 3 parts. The left-hand side is the source, or AKA generator. Generator, that's the signal source. And to the right-hand side is the load, And in the middle is the transmission line. So you have the signal source, transmission line, and the load. That's 3 components, is the 3 basic, that's the 3 basic components of a transmission line circuit. So in this slide, we have a simple question. Supposing that the characteristic impedance of the transmission line system is 15 ohm, the load is 100 ohm. And what is the input impedance at Z equal to 0? Note that in transmission line circuits, you need to specify the length of the transmission line. So in this case, what is the length of the transmission line? L. Okay? So this is defined as Z equal to 0. This point is Z equal to L. So we are asking, the problem is asking the input impedance looking into this. Can you give me a quick answer? What is it? What is the input impedance? 50? 100? 150? Pick your answer, 啊？答案是多少？记住，你是一只小蚂蚁啊，所以答案是50啊。好 ，OK。Well, but this answer is a little bit tricky. It's a little bit tricky. So at the first sight, when you if the switch close up at t equal to 0, then the input impedance looking this way is 50 ohms. Because the transmission line is the only thing you have inside. You can only see the transmission line. You cannot see the load, which is in distance away. Okay? But did you notice what kind of transmission line system exists? Did you notice that this is a battery? This is a battery, DC battery, right? So this is actually a DC circuit. This is actually a DC circuit. So eventually, the load will come into sight. You will see the load eventually. That's what we will. That's what we will have today. We will see what happens as the switch of the transmission line system close up, and what happens. Okay, so at the very moment that the switch is closed, what happened? The battery starts to charging the transmission line circuit. Signal goes into the transmission line, voltage and current flow goes into the line, and at a certain point, with some time delay, it will reach the end of the transmission line, okay? And because the mismatch at the end, because here is 50 ohm, here is 100 ohm, you will have the so-called reflected signal. That is the negative going signal. So the negative going signal will goes back to the source, to the left-hand side. And because suppose the characteristic impedance Z0 and the internal resistance of the generator RG are not the same, you will have another reflected signal due to the impedance mismatch. So you will have signals going back and forth in these systems. However, we know that this is a DC circuit. So eventually, this thing will settle to a conventional lump circuit. So because our signal source is DC. So even though that at the very beginning of the switching process, of the switching on event, due to the event of switching on, we have something going on in this transmission line system, but eventually it will saturate or converge to the DC case. Okay? So that's so this is so-called transient analysis. 所以我们这边要讲的是电路的 transient behavior。transient behavior 这件事情发生的时间很短。我有没有拼对？应该对了哈。transient analysis 。OK， 好，谢谢。transient analysis， 好，毕竟各位都已经学到电磁学第2个学期了哈。所谓的 transient 就是说，这个事情可能发生的时间，根据这个长短嘛，根据这个长短，所以比如说我现在射出一把飞刀，只要飞刀以光速进行的话，你会在10到20，或者是坐后面一点的，你大概有30个 nanosecond 可以反应。所以假如我们的传输线系统的长度是几公尺的话，那么讯号的弹来弹去的时间大概会在几十个 nanosecond 里头完成。所以的所谓的transient behavior， 当然跟你的 L 长度有关，但你可以预期到的是，这样几个来回大概要花多久的时间？几十个 nanosecond， 几百个 nanosecond， 最多1个 microsecond 吧。所以我们在谈的是很小的一段时间 ，OK？ 但有的时候这段时间是重要的 ，OK？ 好。All right, so let's move on to the next page. So we assume that there's no voltage or current on the transmission line for t smaller than 0. And the switch is closed on at t equal to 0. So when t is greater than 0, we will have voltage and current signal going on in the transmission line system. And what happens? What are the variation of voltage and current signal in terms of time and location is referred as the transient analysis. Transient analysis. The characteristic impedance Z sub 0 and the velocity of propagation Vp are very important to the analysis, to the transient analysis. So we will look into this problem starting from t equal to 0. So at t equal to 0, the switch is closed on, so we start to have a positive going signal going into the transmission line system. You can imagine that at t equal to 0, when the switch is closed on, the battery starts to charge the transmission line system. So it needs a positive Z going signal, which we will refer as V plus and I plus, okay? Propagating toward the right-hand side of the transmission line system. So what are the value of V plus and I plus? Well, so to calculate V plus and I plus, we need to take into account the input impedance at this point. That is, the input impedance looking to the right-hand side. So at that very moment, what is the input impedance you have? Z sub 0. You only see the transmission line. So you see the characteristic impedance of the transmission line. So the calculation for the V plus signal and I plus signal are relatively simple. Okay? So you can write up equation using the KVL. So V sub 0 minus I plus times RG minus V plus, which forms a loop. Using Kirchhoff's voltage law, KVL. You can calculate V plus. Well, you also need another relationship to find out the I plus. Okay? What is the relationship between V plus and I plus? V plus is I plus times Z sub 0. So by substituting I plus with this, you end up with these two equations. V plus is V sub 0 times Z sub 0 over RG plus Z sub 0. So providing that you know the characteristic impedance of the transmission line as well as the internal resistance of the generator RG, then you will have V plus. And I plus can be found by dividing V plus with Z sub 0。所以这个称之为什么？其实就分压公式而已嘛。在局部的等效电路，在刚关上的时候，这个地方看到的就是传输线的那个 Z0 嘛，对不对？所以你要算初始的 V plus、I plus 讯号并不困难。Then the positive going signal, V plus and I plus, will propagate along the transmission line. And you will reach to the right-hand side with certain propagation delay. What is the propagation delay? That will be the length of the transmission line, L, divided by velocity of propagation, Vp. So the time delay T, the lowercase t, equals to L divided by Vp. It does not, however, satisfy the boundary condition because it requires the voltage across the load resistance to be equal to the currents. All right. Because originally we only have a V plus and I plus signal. And V plus signal is 50 times I plus. Because of the characteristic impedance, Z sub 0 is 50. However, the load resistance, as we've seen a few slides ahead, RL is 100, which means the voltage across RL should be 100 times the current on RL. So V plus and I plus signals alone cannot satisfy the condition for RL. So it requires an additional voltage and additional current signal so that the total voltage, V plus plus I plus, over the total current, that is I plus plus I minus, equals to RL. Okay? Now, because the load resistance is not the same as Z sub 0, so you will need an additional V minus and I minus term to satisfy the boundary condition at the right end. Okay? So we write up the boundary condition. V plus plus V minus equal to idle times I plus plus I minus. Okay? And we know that the V minus and I minus signal will propagate on the transmission line afterwards. So we can write up the relationship of I minus and V minus, that is I minus equals to minus of V minus divided by Z sub 0. Okay? And I plus can be written as V plus over Z sub 0. So if you replace the I minus and I plus current signal with V plus and V minus signal, you can end up with this equation, and with some massage of the equation. 我不知道为什么美国人喜欢把方程式的整理叫做马杀鸡，OK， 他们基本上用的动词就是 massage the equation a little bit. You end up with this relationship. This is the so-called reflection coefficient. Okay, as you can see, I circle this equation with a red box, which means you need to memorize this relationship. Okay, there's only a few equations that I require you to memorize, and this is one of them. Okay, memorize this relationship. Reflection coefficient, by definition, is the negative going voltage over positive going voltage. And it equals to RL minus Z sub 0 divided by RL plus Z sub 0. 在期中考的时候你会发现我大部分的状况底下改分数是不是那么严苛的啦？多少会改分数，但我深恶痛绝的就是你把向量跟存量搞不清楚。所以你会看到，假如你该写向量写成存量，或该写存量写成向量，我扣分会相对比较重，好不好？所以向量、存量要搞清楚。这个东西反射系数，它的计算是从你假如要从第一段看往第二段的话，这边看过去的，它的反射计算是对面那一段扣去自己这一段的，除上后面那一段加这一段，所以你会看到这边是 RL Z0， 所以我现在看的是这边，从这里往这边看，所以是从分子的地方比较重要嘛。分子的地方因为有个 minus sign， 所以是 RL 减去 Z0，RL 减去 Z0， 看过去的那边的地方扣掉你自己这边的地方，然后除上，两者相加。好，你要是这个顺序写反，那就是全扣了。我再三提醒因为我们